Today we are going to show you a demo of how to deploy a trial network connected to external equipment, and specifically a Nokia radio in the platform of the University of Malaga. Before start, let's remember what a trial network is by definition. We talk about flexible networks and configurable networks that can combine and help us to validate technologies related to 5G and 6G. These networks have to be versatile in terms of technologies, components, experimental processes, and metrics obtained. This demo shows the deployment of a trial network. This is the diagram of what we are going to deploy, and we can see what would be the container of the trial network, where the 5G network core is going to be deployed in a Kubernetes cluster. On the other side, we have a physical Nokia radio connected to the site network of the Malaga platform. A user equipment is also connected to another network of the platform. What we are going to achieve in this trial network is to connect the Nokia radio with the core 5G that we are going to deploy inside the Kubernetes cluster. On the other hand, we will connect the user equipment to the Nokia radio, and we will show how it is capable of browsing the internet. It is important to remember that this trial network is a special one, because several reasons. The first is that we are using physical components with a static configuration that cannot modify during the deployment of the trial network. The second particular point is that a trial network has to be isolated by design, so that it does not interfere with other trial networks. So, we will need to manage the trial network networking with the Bastion machine that will be in charge of isolate network components and traffic. To design a trial network, you have to use the components offered in the 6G library. Then a trial network has to be able to be represented through a descriptor file that includes several components from the 6G library, their relationships and dependencies. We can take a look to the Open 5GS component in the 6G library GitHub repository. In the file called public YAML, we have all the information related to component metadata, input and output variables. Here we can review the variables, their type, if they are required or not. These variables have to be synced with the ones in the trial network descriptor file, where the structure of each component has to be included. The trial network descriptor file should contain all the components with the correct values for the inputs required, and the dependencies between them well defined. In the case of the trial network that we are going to deploy for this demo, we have a series of components mandatory such as the TN init and the virtual net, that are needed to create the virtual container of the trial network, but also we're going to deploy a Kubernetes cluster that actually is a dependency of the Open 5G core, because we deploy the version based on microservices and compatible with the cloud-native model. Additionally, we also indicate here the Nokia radio component and the user equipment component. Once this descriptor file is complete, it is passed to the TNLCM that is responsible for controlling the lifecycle of the trial networks. First of all, it will try to validate the format and then define the component's deployment order, according to the dependencies that we have indicated. In this slide we can see the flow of what will occur during the deployment of the trial network and the tools that we are going to use during the deployment. So first of all, we will have an experimenter creating the trial network. This will be the first moment when there is an integration with the 6G library, since the experiment has to consult the 6G library to learn about the components available. Once the trial network descriptor file is complete, it is sent to the TNLCM, which is in charge of validating it and define the order of the components to be deployed. The deployment is sequential one by one, and as you can see, there is also an integration with the 6G library and both TNLCM and Jenkins, which is going to be the orchestration tool in charge of the correct deployment of each component. Every time the TNLCM orders the deployment of one of the components, a pipeline is executed by Jenkins, so that the code inside this component related to infrastructure creation and configuration is executed, and it relies on a couple of well-known tools. On one side, Terraform, which is the tool that we use to create the virtual infrastructure in the private cloud. The private cloud is managed with OpenNebula project. On the other side, Ansible is the tool selected to complete the configuration of each component, even the configuration of other component or platform equipments. When deployment begins, each component is deployed and the results of its deployment, together with the most relevant information for the experimenter, is stored in another tool called Mini.io, where we store all the descriptors, manifestos and other important information that will be necessary to keep the trial network status, and also to generate a report that will be sent to the experimenter with relevant information to be able to operate the trial network. The first thing to do to deploy a trial network using the TNLCM is defining a descriptor. The descriptor is a YAML file including all the components inside a trial network. Each component declares its dependencies and its input values. For this demo, the components are going to be the TN init, which includes the Bastion VM and the trial network VXLAN. The VINIT is the internal network for the Kubernetes nodes. 1KE is the Kubernetes cluster inside OpenNebula. And Open5GS is the 5G core which will run inside the Kubernetes cluster. Finally, we have the Nokia_radio and the UE components. For this demo, we had to make sure that the 5G core attributes matched the configuration of the physical Nokia radio. To deploy the trial network, we go to the TNLCM. The first step is to log in and enter the authentication token. To do that, first enter your user credentials. Then, throw a login post request. Copy the access token and paste it here after typing bearer. Now, we can define the trial network inside the TNLCM. Enter a TN ID, your site, and alternative repository branches if you need to. Finally, upload the trial network descriptor. After the trial network is successfully defined in the TNLCM, we can deploy it with a put request. Just type the TN ID and the Jenkins pipeline name if you are using a non-default one. The TNLCM will start launching a Jenkins job for each component sequentially. The Jenkins UI can show the deployment output for each component. As you can see, the Jenkins pipeline first configures its environment, and then launches the Ansible playbook for each component. The deployment process can take a while to set everything up. For this demo, we'll have to wait for 6 separate Jenkins jobs. Once the deployments are finished, we can check in the OpenNebula that the virtualized infrastructure is successfully created. There's the Bastion VM for our trial network, and the 6 VMs of 1KE. The 1KE service, administrating the Kubernetes cluster. And 2 VNets, one for the trial network and one internal for the 1KE. Lastly, and until the TNLCM frontend is able to show them, we can find in the min.io a markdown file per each one of the components deployed, with information about its parameters and general usage. For this demo, we'll download the files for the TN init, the 1KE, and the physical user equipment. The tn-init file includes the SSH key pair to access the TN VMs. The 1KE file shows the token to access the schooner dashboard inside the cluster. And the STF UE file shows the credentials to login into the STF web portal. As an experimenter, the first thing I need to do is connect to the VPN using the WireGuard configuration that I've downloaded from the manifests and the Bastion information. This will give me access to all the components and services in my trial network. Now that I'm connected, I will open my browser and access the Kubernetes dashboard called Schooner. Here, I'll show you the nodes in my cluster. There are a total of 5 nodes, 1 master, 1 worker node, and 3 nodes dedicated to Longhorn storage. Next, I'm going to open the Open 5GS namespace, where we can take a look at the network functions that contains my Open 5GS core. Now, I'll open the AMF pod and show you the logs of this function. Here, you can see that the AMF has detected a connection with a G-node B, which in this case, is the Nokia Malaga radio. I'm now going to switch tabs and enter the Open 5GS dashboard. Here, you can see the subscription of a SIM card and some information as the IMSI and the slice. This SIM card is the one that contains the physical UE that I will show you now. I'll switch to another tab to show you a tool called STF, which allows me to remotely control my physical UE. I am going to turn off airplane mode on the device, and you'll see how the UE connects to the network. As you can see, it also has 5G connectivity. Once connected to the network, we can test the internet connection by opening the web page of the project 6G-SANDBOX. I am now going to open another application on my smartphone to see some more information such as my IP address, where you can see that it is 10.45.0.2. Finally, I am going to run a speed test on the device to check the uplink and downlink throughput. Then, I'll go back to the Schooner dashboard to check the AMF logs again, where we can confirm that a UE has been registered in the core. If I go into the UPF logs, I can see the IP of the UE that has connected, where I can see that it is the one we have seen previously, 10.45.0.2.